So I won't be here tomorrow. So tomorrow in class, you'll be working on some practice over what we talked about today, which is a lot of mathematical stuff. And then you'll also have some time to work on those notes over 7.4. So no, they're not technically homework tonight, but if you're let me get ahead of the game, then that's what I recommend. Okay, so 7.3 goes over a few very big things that we need to know, especially moving into stoichiometry, which is about a chapter away. This is the precursor chapter to the let's balance equations and write out chemical equations. And there's a reason you've been going over the naming again, and that has to do with the fact that when we start balancing equations, we have to be able to recognize names and formulas and vice versa, just in case. Okay, so that being said, let's talk a little bit about chemical formulas. Okay, what are the purposes of our chemical formulas? This is going to tell us what elements exist in a compound. Pretend that's an element. CMPD means compound. And how many of each element. Okay. They give us the ability to calculate a few things, okay? First is going to be what we call the formula mass. And I'll remind you that formula masses have a unit of AMU. They're going to give us the ability to calculate molar masses, which have units of grams per mole. These two are very similar. Whatever process we use for one, we're going to use for the other. The only thing that's going to be different is going to be the unit. And then the last thing, and the last topic of today's lecture, will be the percentage composition. This is where we take an element's mass and we try to figure out what percentage of that compound is given to one single element. Okay? All right. Let's talk formula mass. So formula mass is going to be the sum of the average atomic masses of the elements present by number. So in other words, quantity matters here. Okay? We talk about H2O. The fact that there are two hydrogens in H2O means that when we calculate the formula mass of the compound, that we have to multiply the mass of one hydrogen by 2. That's all that means. Okay? Where do we get formula masses for individual elements from? Periodic table. On my periodic table, those are the red masses. Okay, so a hydrogen atom has a mass of 1.00795. An oxygen atom has a mass of 15.998. And again, since we're dealing with formula weights, our unit is in AMU. Now in H2O, there are 2 hydrogens and 1 oxygen. Do you agree?
Yes.
Okay. So we're going to multiply this one times 2. Gonna want your calculator out today. All right, so when I'm trying to find the formula weight, or formula mass, if you will, of H2O, I'm going to add those two numbers together. Ooh, what a good question I was just about to ask. Do the formulas, or I'm sorry, the masses on the periodic table have sig figs? Those are constants, right? What do we learn about constants and sig figs? They don't. So there are no sig figs here. Okay. What I would say the general rule of thumb is whichever one has the most decimals, that should be the one that you kind of go to, right? In this particular case, my calculator spit out 4 decimals, so I just kept 4 decimals. Okay. A lot of times you will be using a periodic table that has no more than 4 decimals on a mass, so just carry it to 4 when you're done. Okay. You'll also hear me sometimes say rounded 2 decimals because that's just easier and it makes things a little bit less precise, so that it'll help account for errors. Now, if you had a different periodic table and you came up with this, are you wrong? No. If you had a different periodic table and you came up with this, are you wrong? Yeah. So understand that there is this margin of error, and we need to make sure that we pay attention. There are no sig figs here. That does not mean we're getting rid of sig figs. It just means that with formula weights, molar masses, and percentage compositions, there are no sig figs. This is the first part of the math that we're going to be doing. Okay. Next thing's going to be a molar mass or a molecular mass. AKA the mass of one molecule. Again, this is just another way to describe a formula mass. Okay, so when you hear the term molecular mass, it is not the same thing as a molar mass. We're talking about the mass of a molecule. Okay. I'm going to let you do one on your own. Okay, so that's a CL, just so we understand. Who wants periodic table? Because you can't see. Also, Miss Valentine, you forgot your plans. She was very mad. I'm kidding. She was so funny. I'm going to assume, Sean, you don't. Would you like another? Exactly. So, yeah, so we'll talk about that here in a second. I want you to do this one first. What's the name of this item? Potassium chlorate. Nice. Thank you for recognizing that that is a polyatomic ion. Remember that your unit should be AMU. up, Braden?
Do you want us to do like the 2 times hydrogen before the problem?
Only if there's hydrogen. Remember, the only reason we did this is because this formula says H2. So you're using this formula instead. Right? So there is no hydrogen in this one. Instead, what are you going to multiply something by in this one?
I think he means like.
I mean, like as an example.
Do we have to like?
Oh, no. No. You can just go, you could skip to here and do 2 times H plus 1 times O and then do the math. And
Okay.
you don't have to do that. That was me being, here are those masses. No. Pretty soon you're going to get to the point where you don't even have to show your work to do this. So right now we're just working on, let's learn a concept. All right, check your answer. Are you close? That's okay. Remember, as long as you're close, you're good. We have to learn to like be okay with numbers that are slightly different than other numbers. It's okay. All right, let's move on. Let's talk about the molar mass of something. In the past, we talked about a mole of, say, gold atoms would be a certain number of gold atoms. Okay, so I'm going to draw pictures here to illustrate a concept. A gold atom. A gold atom. Okay? All right, if I say I have a mole of H2O, Mickey Mouse. It's really what water looks like is Mickey Mouse. So if I say I have a mole of H2O atoms, what I'm saying is I have that many H2O atoms. In other words, if I could, I would draw you a whole bunch of Mickey Mouse atoms, right? Okay, so if I say I have a mole of this, I have 6.022 times 10 to the 23rd. If I say I have a mole of these compounds, I have 6.022 times 10 to the 23rd of those compounds. Understand? Okay. The mass of a mole of either an individual element or a compound, leave my mass up there for a second. Okay, the mass of that compound is going to be equal to the same thing as the formula weight. What we're going to do is we're going to take the amount of AMU, and we're just going to convert the unit to grams per mole. So for instance, let's go with H2O. We calculated that at the beginning of class. We said it was 18 point, anybody remember? 013. We said it was 18.013 AMU. Well, yeah. Okay. All I have to do is change the unit to know how much 1 mole of water will weigh. So if I take a beaker and I put it on a balance and I add 18.0139 grams to that balance, I have 1 mole of water molecules in that beaker. Okay? So, hopefully you see that a molar mass is useful because we can measure it on a bench. A formula mass, not so much. Knowing the mass of a single atom or a single compound is nice, but not terribly useful when it comes to bench chemistry, which is what we do. Okay? Okay. So we just did this relation. Let's do another problem. And we're going to do this one together. So we're going to follow the exact same procedure that we followed for the formula mass, except that in this particular case, we're just going to change the unit. Now, before we do that, what does that 2 do? That 2 is going to multiply everything inside of the parentheses by 2. So, in other words, the compound that we need to find the mass of is really this. Okay, there's 2 approaches to these types of formula masses or these types of molar masses. The first is to just distribute the subscript that's outside of the parentheses inside to the different polyatomic ions. We don't like to do that in chemistry, but you're more than welcome to do so. The second approach is to figure out the molar mass of just the NO3 and multiply the whole thing by 2. Both ways will get you the right answer both times. Okay? So I'm going to go through this route. You can probably see how they can get very complicated very quickly, right? You've seen some of your polyatomic ions have a lot of atoms in them. Think of acetate. Put a 4 out here and you're calculating something pretty big, right? You will see numbers that are pretty large, and that's really just there to see if you can understand the concept behind what is a molar mass. Okay. So, my barium has a mass of 137.327. I want to know what my mass of NO3 is. Now I'm going to try to bring it all together. Dropping my numbers down. $124. What's our final answer? Anybody? What'd you say? Yeah, that sounds about right. What's our unit? Grams per mole. Remember, we're going for molar mass. That was the hard stuff. All right. That was the, yeah. We are going to go over the review of molar mass conversions. So, I'm going to remind you, last semester, yes, I said it out loud, we talked about how to convert an amount of grams to moles, right? What was involved in that process? Grams and moles, good. Be more specific. Conversion factors. Woo! So, our molar masses are conversion factors. Just remember this. Can I erase? We good? Good? Well, let's do a review one. Okay. With our singular oxygen atom, what are the two conversion factors? Yup. When we set these problems up, we followed a specific set of steps on purpose. Or, I'm sorry, we did like given. Okay, so what's our given information? 2.5 moles. Okay. Step 2 was identify goal. What's our goal? Number of grams of O. Okay. Then we had step 3 was like, what do we need? And that's where we said the conversion factors. Or if we were working on a problem that had like an equation, we would also need the equation. Right, so that's what went there. For us, in this problem, we only need the conversion factors, right? Okay. And then step 4 is to set it up with your given first. Right? So we're going to start with our given number. We're going to use the box method because we love the box method in chemistry. Your given number is always the first one. Remember, there's like nothing underneath. Or if you're really one of those people who needs to put something underneath, you just put a 1, no unit. Okay? Then we're going to multiply by a conversion factor that will cancel out the moles and leave behind grams on the top of the fraction. So which of the ones are we going to pick, the left or the right of the conversion factors? The one on the left. Brief review, because the next thing we're going to do is we're going to use the actual molar mass of a compound to do the same exact type of process. Okay? Then when we do this, we multiply across, right? So we do 2.5 times 15.9994, all divided by 1. And then what do we get? I did that on purpose. 3 9s? Here's a question.
It's 39.
Oh. Okay. Sig figs?
Yes.
Yes. How many sig figs? 3. 3 is the correct answer. Where did the 3 sig figs come from? The 2.50. Remember that your masses from the periodic table do not count. So, remember to add a unit. In this case, it was grams of oxygen. Okay, now let's do one with a compound. Because we already have the molar mass and we wrote out the conversion factors, I'm going to have us do a problem with that. Okay, how many grams in 2.5 moles of BaNO32? So the first thing is, what's our given? Of the barium nitrate. Okay. What's our goal? Like it. Do we have the conversion factors already? We're good. Next thing is going to be to set it up with a given first. I'm going to do it over here. So my given information is the 2.50 moles. That's a long one. All right. Are we going to choose the conversion factor on the left or the conversion factor on the right? I hear left. Raise your hand if you agree. Okay, let's do it. Ta-da, ta-da, look at that. Moles cancel. All right, so then we plug it into our calculators and we get this. Remember, we cross multiply, so we're going to multiply across. How are we doing? Ooh. He's doing so well. Got kicked him. What's the answer?
653.
You stopping there? 3 sig figs, right? Don't forget your unit. Part of your unit is the name of the substance. The unit is not just grams, it's grams of barium nitrate. So part of your unit is always the substance you're calculating. All right. How do you feel about that? Pretty good?
Yep.
It's not too difficult, but it is something to pull out of your brain from last semester. Okay. Now let's do another thing. One more thing. I say one more thing, but I feel like it's probably not. Yep. Last topic in this section is percentage composition. This is used to describe the portion of a compound that is dedicated to one element. So for instance, if I say the compound is that gives you some information. What we have to determine is how to use that information or what to do with that information. What we're going to work on in this particular section is calculating the percentage given a molar mass. In the future, what will be given is a percentage and asked to figure out what the formula is. And again, processes. Okay? So the first thing you need to know the formula of your compound. So in other words, if I give you a name, you have to know the formula. Anybody want to take a stab at it? Li3 PO4. Because the charge on a phosphate is 3 minus and the charge on a lithium is a 1 plus. Okay? All right, second thing you need to do, calculate the molar mass. Okay, so work on that. Yeah.
So we have to find the formula mass first, and then.
You can just use the same process for formula mass as molar mass. So whatever you would have done to find the formula mass, you do for the molar mass too.
But you just change it.
You just change the unit to grams per mole. Yeah. Does that make sense?
Yeah.
So the short answer is no. Though if you do that, you just change the unit at the end. It's up to you. That's a good question. Ava asked, so one of the masses of these things on your periodic table has 6 decimals. I would never use more than 4. Beyond that, you're just getting nitpicky. And remember, they're no more significant than anything else, so. Who is a molar mass for lithium phosphate for me? Anybody? 0.79. What do you have on? Thank you. Everybody agree? Whoa. Cool. Go ahead.
115.7943.
You got one? Okay, so wait, let's see what happened. So the lithium, hey, check this for me. 6.941. The phosphorus should have been 30.973. Just check your calculator. And then the O times 4 should have been the 15.99. 4 times 4. Well, that's 60 plus 30, that's 90. Yeah, I think 115 is probably closer. Did you mess up a decimal somewhere?
Oh, I put 9.9.176.
Yeah.
That's why I just put
Okay.
it on number.
That's why we do them out loud. 115 point. What was it? Oh, okay. Just want to make sure. All right. There we are. Next thing we're going to do is we're going to calculate the percentage of each individual element by knowing what their individual contributions are to the molar mass. So this is where the method of calculating what just lithium's mass is and then what just phosphorus's mass is and what just oxygen's is going to be useful when you're adding them up. Yes?
So is it like just like one lithium or the three?
All three by number, right? So I want to know the total mass of lithium in this compound by knowing how much all of the lithium weighs compared to the total molar mass of the lithium. So for this one, we get 20.823. This one just stays the same. This one I got 63.9976. Okay, so just looking at these numbers, what element should have the highest percentage? The oxygen, right? Okay, so next thing we're going to do is we're going to calculate our percentages. We're going to take the mass of the element for each one, divide by the molar mass, multiply by 100. You're going to get 3 percentages here. Okay? So I'm going to do... Okay, who has a mass or a percentage for lithium? Go ahead.
17.98.
17 point what?
98.
And remember, since we're using masses from the periodic table, there are no sig figs here. When in doubt on a percentage, carry to 2 decimals. Just always carry 2 decimals. It's the kind of thing I'm always reminding you of. Someone's always like, what are we rounding it to? Always 2 decimals when in doubt. All right, what's my percentage on phosphorus? Anybody? Krista?
26.75.
Say 26? Okay. All right, and then for oxygen, anybody?
27.
Okay. Hopefully your numbers agreed? Yes? Good. Questions? No? You do not have homework tonight. If you want to get a jump on your reading, which is due on Saturday, because I want to be able to talk about it on Monday, and I don't really want to say I gave you homework on Friday. Yeah, I like to get around those numbers. Plus, if I make it due on Saturday, then you won't be doing my homework on Sunday. Right? You're all going to do it tonight. Like, I don't... I just make... You want me to make it due tomorrow? Or do you want to, like, have the satisfaction of turning it in early? Like, I don't...